Hello friends, let us take one concept in derivative, applications of derivative, and that is Rolle's theorem. So we take the concept here of Rolle's theorem, and I just say strictly also that you write in your notebook also, and this is exactly the things that is in our syllabus. So first we take the statement of the theorem. The theorem says like this. So let f be a real valued function defined on the interval AB such that first it is continuous on closed interval AB. Second, it is differentiable on open interval AB. And third, f of A equal to f of B. So if these three conditions satisfied, then there exists a number C in between A to B such that f dash C, that means derivative of f at C, is 0. So this is the statement of the theorem. So if a function satisfies these three conditions, that is continuous on closed interval AB, differentiable on open interval AB, and f of A equal to f of B, then there must exist at least point C. So it may be more than one point also exist. Then there exists a number C, or you can say that there exists at least one C belongs to AB such that f dash C equal to 0. Now we know what is the f dash x. So f dash x is nothing but the tangent. Okay, if I say f dash C, then it is nothing but the tangent, slope of tangent at CFC, that is f dash C. F dash C meaning it is a slope of tangent at the point CFC. Now the slope of tangent at the point CFC equal to 0, meaning what? So it's a geometrical meaning, slope is 0. That means it's a parallel to x-axis. So it's like this. See, the Rolle's theorem is now geometrically what it says. It says like this: if the function is continuous from A in a closed interval A to B, it's a differentiable, and fa equal to fb. So this ordinate is fa and this ordinate is fb. So the length, that means this fa and fb are equal, then there exists a point C in A to B such that f dash C equal to 0. That means this f dash C, that means equal to 0, means it's a slope of tangent is 0, that means parallel to x-axis. So it's like this. at least one c, that means there may exist more than one c. So just we simple take example like sin x plus 2 and we take in 0 to 2 pi. Then in 0, at 0 sin 0 is 0, f0 is 2, at 2 pi also 2. So conditions of Rolle's theorem satisfied, and you can see that here we are getting c at pi by 2, here also we are getting c at 3 pi by 2, so we may get more than one c also. So this is the Rolle's theorem. Now one more, so this is geometrical meaning. This is nothing but the geometrical meaning. Now there is also one very good algebraic meaning. Sometimes those kind of examples are there in JEE also. Algebraic meaning is like this. Say suppose you are having fx and that is a polynomial, and we know that polynomial is a continuous and differentiable function. Suppose that polynomial fx has two roots at a and b. What does it mean? It means that fa equal to 0, fb also equal to 0. So see, the polynomial is continuous, differentiable, and fa equal to fb. That means the conditions of Rolle's theorem satisfied. So what does it says then? It says like this. Then there exists c belongs to ab such that f dash c equal to 0. Can we say like this? C is a root of f dash x. C is a root of f dash x. So what does it mean? It means like this. Between, so this is the geometric algebraic interpretation. Between any two roots of a polynomial, say fx, there is always a root of f dash x. Okay. Now Rolle's theorem, there are two kinds of examples, two types of examples are there. One is applicability of the Rolle's theorem. So you need to check whether the Rolle's theorem satisfied, or means conditions of Rolle's theorem satisfied or not. That means continuous in closed interval, differentiable in open interval, at endpoints the value are same, fa equal to fb. So that is called the applicability of the Rolle's theorem. And second is verify Rolle's theorem. Second is verify Rolle's theorem. That means if the function satisfied all the properties of Rolle's theorem, then there must exist c belongs to the interval ab such that f dash c equal to 0. So to find the c is nothing but the verification of the Rolle's theorem. Okay, before starting the examples, let us recall that some of the things we know. The first is a polynomial function. If you are given any polynomial function, you can directly write it's continuous and differentiable. So a polynomial function is continuous and differentiable always. Then the exponential function e power x, then say sin x, then say cosine x are continuous and differentiable on R. Even a power x is also. Then say some trigonometric functions, say tan x, cot x, sec x, cosec x, they are also continuous and differentiable in their domains. Do take care, they are not continuous on R, because say tan x, so tan pi by 2 is not defined, infinity. So tan is not continuous at pi by 2. But if I write domain, then that wherever the tan function is not defined, that point is not there in the domain. Then similarly log also, log function is also continuous and differentiable in its domain. So we do what we do, say tan. So tan is not continuous, say at x equal to, you can take pi by 2, 3 pi by 2 and so on. But those points are not in their domain. Similarly, say some of the things we need to remember, like fx equal to modulus x. This is a standard function. This function is continuous on R, but not differentiable at 0. So this fx equal to modulus x is not differentiable at 0. In particular, modulus x minus a is not differentiable at x equal to a. Okay. One more thing is, if suppose some f dash x is there, and if f dash x say tends to infinity or minus infinity, say at some x tends to k, then you can say that fx is not differentiable at x equal to k. So just give an example. Suppose our fx is like say 2x minus 1 power 1 by 2. What is f dash x? So f dash x is 1 by 2, 2x minus 1, power 1 by 2 minus 1, and the derivative of 2x minus 1 is 2. So is it 1 upon 2x minus 1 power 1 by 2? So we can say that this is not differentiable at x equal to 1 by 2, because at 1 by 2 f dash 1 by 2 tends to infinity. So f dash 1 by 2 tends to infinity, therefore f is not differentiable at x equal to 1 by 2. Such kind of examples are also there. One more result also we know, say some difference, then product, then quotient of continuous, even differentiable also, functions is continuous or differentiable. What does it mean? It means that if there are two functions which are continuous, their sum, difference, product, quotient also continuous. If there are two functions which are differentiable, then their sum, difference, product and quotients are also differentiable. So let us now, we are in a position to solve some examples. So let us take the first kind of examples, like check the applicability of the Rolle's theorem. So let us solve one example then. The question is, discuss the applicability of Rolle's theorem for the following functions. Okay, we are having 2-3 examples. Let us take first one, fx equal to modulus x, and the interval you are given as -1, 1 close interval. So how to write in exam, that also you should. So if this kind of example asks, it will ask for 1 mark, and for 1 mark example you can write even 1 line answer also. See, we know that this function is not differentiable at x equal to 0. You can have like this, fx is equal to x when x greater than or equal to 0. That means we are given in -1 to 1. So can we write like this, when x greater than or equal to 0 means when x belongs to say 0 to 1, and minus x when x belongs to -1 to 0. 0 you can take here close, open, any one side you need to take 0 as a close. Okay, now it is easy to see what is f dash x. F dash x is 1 here when x is in 0 to 1, and -1 when x is in -1 to 0. Now, so see, f dash 0 is not possible because right side derivative, right side f dash 0 is 1 and left side f dash 0 is -1. That means f is not differentiable at x equal to 0, and that 0 lying in open interval -1 to 1. So what do we write now? We should write like the final answer is the Rolle's theorem is not applicable to this function. So hence Rolle's theorem is not applicable to fx equal to modulus x in close interval -1 to 1. Let us take one more. So second example is fx equal to 3 plus x minus 2 power 2 by 3, and the interval is given as 1 to 3. Now here we can easily see that it's a continuous, but let us try for its derivative. So its derivative is 0 here, plus 2 by 3 x minus 2 power 2 by 3 minus 1. So what does this mean? It is 2 over 3 x minus 2 power 1 by 3. Okay, so what do we then say? At 2 the derivative becomes infinity, and 2 lying in the interval 1 to 3. So we see that f dash 2 tends to infinite, or you can say f dash 2 not defined. as x tends to 2. Therefore, f is not differentiable at x equal to 2, and that is belongs to open interval 1 to 3. When we are writing about derivative, we write open interval, okay, because the conditions are also like this, that f is differentiable in open interval AB, okay. So f is not differentiable at x equal to 2, so therefore Rolle's theorem is not applicable to fx equal to 3 plus x minus 2 power 2 by 3 on 1 to 3. Do write completely. You should not write like Rolle's theorem is not applicable to function fx equal to 3 plus x minus 2 power 2 by 3. Because this interval is important. In this interval it is not applicable. In other interval it may be applicable. So you need to write completely. So third one. Fx equal to say 10x, and the interval considering as 0 to pi. So here also we can write in a one line, because you know 10 pi by 2 is not defined, okay, and pi by 2 is given in that interval 0 to pi. So we directly write we know that x is not continuous at x equal to pi by 2, and that is belongs to 0 to pi. Okay, for continuous we write closed interval, and therefore Rolle's theorem is not applicable to fx equal to 10x in 0 to pi. Okay, so let us take one example then. The question is like this: discuss the applicability of Rolle's theorem for fx equal to x square plus 1 in 0 less than or equal to x less than or equal to 1, and 3 minus x in 1 less than x less than or equal to 2. See, this function is that means we are given the interval as 0 to 2. So basically if this function is either not continuous or not differentiable, it is only at one place and only at x equal to 1. We need to check only at x equal to 1. So see, at x equal to 1, here the value is 2. And at x equal to 1, here also the value is 2. That means at 1 the function left side and right side same, that means it's continuous, because when we draw the graph we don't need to lift pen from the paper at x equal to 1. At x equal to 1 left side, right side the value is same, so it's continuous. But let us see what about differentiable. So f dash x is set 2x here in 0 to 1, and this is minus 1 at 1 to 2. Now what about left derivative at 1? So left derivative at 1 is 2 and right derivative at 1. So right derivative at 1 is minus 1. What does it mean? Therefore f dash 1 left derivative and right derivative are not equal, and therefore f is not differentiable at x equal to 1 and 1 lying in the interval 0 to 2. Therefore, Rolle's theorem is not applicable to given function on 0 to 2. Okay, now let us take the kind of examples where we need to verify the Rolle's theorem. Do remember, in exam there is another concept that is called mean value theorem. So one example will definitely ask either of Rolle's theorem or mean value theorem. So the question is, this was asked in CBSE paper 2002, that verify Rolle's theorem for fx equal to x square minus 5x plus 6 on close interval 2 to 3. So let us see how we can solve this example now. So fx equal to x square minus 5x plus 6, and the interval we are given is 2 to 3. Now we write like this: f being a polynomial is continuous on close 2 to 3, second, differentiable on open interval 2 to 3, and now we need to find f2 and then f3 also. So we need to check whether fa and fb are equal or not. So if you write f2, then it is 2 square minus 5 into 2 plus 6. Okay, and what is that value? 0. Let us see f3. So 3 square minus 5 into 3 plus 6, that is also 0. So therefore f2 equal to f3. So this is third condition, and therefore the conditions of Rolle's theorem satisfied. So Rolle's theorem applicable. So conditions of Rolle's theorem are satisfied. Now once the conditions of Rolle's theorem satisfied, then we need to find out C in the open interval 2 to 3 such that f dash c equal to 0. So now fx is equal to x square minus 5x plus 6. F dash x is 2x minus 5. So f dash c is 2c minus pi, and if it is equal to 0, then c equal to 5 by 2. Does 5 by 2 lying in the open interval 2 to 5, 2 to 3? Answer is yes. So it belongs to open interval 2 to 3. So what does it mean? Therefore, for c equal to 5 by 2, f dash c equal to 0. Hence, and that 5 by 2 lying in the interval 2 to 3. Hence, Rolle's theorem is verified. Okay. Take one more example. Verify Rolle's theorem for fx equal to x into x minus 3 square from 0 less than equal to x less than or equal 3. Okay, so that is 0 to open close interval 0 to 3. So now the function is x into x minus 3 square, and you are given interval as 0 to 3. So same way, this is also similar to the example like x square minus 6x plus 9. So you can write x cube minus 6x square and plus 9x. Same way, this is also a polynomial, so we can also write in the same way, like f being a polynomial. So f being a polynomial is continuous on close 0 to 3, second, differentiable on open interval 0 to 3, and now we need to check whether it is the value at 0 and at 3 equal or not. So f0, so function fx is x cube minus 6x square plus 9x, so f0 is 0, and f3, so that also you can have, you can write here also x minus 3 square, that would be more better, to x into x minus 3 square. So f3 is also 0. Okay, so that means f0 equal to f3, and therefore conditions of Rolle's theorem are satisfied. So conditions of Rolle's theorem are satisfied. Now we need to find f dash c, whether that c lying in the f dash c equal to 0. So first let us find f dash x. So what is fx? Fx is either you write this one or this one, x cube minus 6x square plus 9x. So f dash x is 3x square minus 12x plus 9. Okay, so f dash c is 3c square minus 12c plus 9. Okay, so we need to find the c. So f dash c equal to 0, so will imply c square minus 4c plus 3 equal to 0. We can easily factorize 3 ones are 3 minus 3 minus 1. So c minus 3 C minus 1 equal to 0, and therefore C equal to 1, comma 3. Now we are getting two values of C, but it may happen that both values are possible. It may happen that only one value possible. It will never happen that both values are not possible, because conditions of Rolle's theorem are satisfied. Now the interval is 0 to 3. Open interval we need to consider. So this 3 will not be considered. So here C equal to 1 belongs to open interval 0 to 3. So this is our required C. So what does it mean? Therefore, at C equal to 1, f dash C equal to 0. Hence Rolle's theorem is verified. Okay. We take one more example. Verify Rolle's theorem for fx equal to x cube minus 6x square plus 11x minus 6 on close interval 1 to 3. So let us see here, fx equal to x cube minus 6x square plus 11x minus 6, and the interval is 1 to 3. Now f being a polynomial is 1. Continuous on close 1 to 3, second, differentiable on open interval 1 to 3, and third, f1 is 1 cube minus 6 into 1 square plus 11 into 1 minus 6. So what is f1? f1 you can find. So 11, 12, so it is 0. Then f3, so it is 3 cube minus 6 into 3 square, 11 into 3 minus 6. Check yourself, it is also 0. So here f1 equal to f3, and therefore conditions of Rolle's theorem satisfied. Now f dash x. So fx you are given x cube minus 6x square plus 11x minus 6. So f dash x is 3x square minus 12x plus 11. F dash c equal to 0 will imply 3c square minus 12c plus 11 equal to 0. And this would imply c equal to, now we need to apply ax square plus bx plus c equal to 0. Then x equal to minus b plus minus root b square minus 4ac divided by 2a. So c equal to 12 plus minus root 144 minus 4, a is 3, c is 11 upon 2a, so 2 into 3. And you need to verify, you need to check this c is equal to, we are getting 2 plus minus 1 by root 3. You can verify this, it's not difficult. Now see, what we are given interval is 1, 2, 3. So 2 plus 1 by root 3 lying in this interval 1, 2, 3, answer is yes. 2 minus 1 by root 3 also lying in that. So both value here lying in 1, 2, 3. 2 plus something, 2 minus. So here we are getting two values. It's okay. So therefore for C equal to 2 plus minus 1 by root 3, f dash C equal to 0. And therefore Rolle's theorem is verified.